Hello, in this video we are going to go over something called electronegativity and bond polarity. So in this chapter so far, we said that in covalent bonding, atoms are sharing electrons. However, electrons are not always shared equally between the two atoms. Now, let's say we have two of the same atom. For example, in the molecule H2, we had two hydrogens. Now, in that case, the electrons will be shared equally because the atoms are exactly the same. But let's say the atoms are not the same. There are cases where one atom likes electrons more than the other atom, and so those electrons are going to hang out with that atom a little bit more. So for example, down below, I've got H2 on the left, and this is an electron density map. So this is showing where electrons are hanging out. Now you'll notice that the color is equal across that shape. So that means that the electrons are hanging out with both atoms equally. In the molecule on the right, HCl, we can see that there's a little bit more density around chlorine. So the shape is a little bit bigger around chlorine. And that means that electrons are hanging out with chlorine more often than they're hanging out with hydrogen. And that's because chlorine likes electrons more than hydrogen does. So the electrons are not shared equally between hydrogen and chlorine. They're still shared, just not equally. So on the left, because the electrons are shared equally, we're going to call this covalent bond a non-polar covalent bond. And then in HCl, because the two electrons are not shared equally, we're going to call that a polar covalent bond. All right, so again, a covalent bond that has an equal sharing of electrons is called a non-polar covalent bond. And then a covalent bond that has an unequal sharing of electrons is called a polar covalent bond. So how do we represent that difference in bond or electron sharing? So the imbalance in electron density results in a buildup of partial negative charge on one side of the bond and a partial positive charge on the other side of the bond. So if electrons are hanging out with chlorine more often, that means there's more negative charges on chlorine's side of the molecule. And if they're not hanging out with hydrogen as often, that means hydrogen doesn't have as much negative charge on its side of the molecule, so it has more of a positive charge. So we indicate partial negative and partial positive charges with these little delta symbols here and here. And then we put a positive or negative next to it to indicate what that partial charge is. Now, the other way to represent it is with an arrow. And down below you can see we've got this arrow here pointing towards chlorine. So that's showing the direction that electrons are typically moving in. And then we put a little positive charge on the side that electrons don't hang out as often. So this separation of charge results in what's called an electric dipole. So again, the direction of the arrow is pointed toward the partial negative end, while the positive tail indicates the partial positive end. So again, chlorine likes electrons more, and hydrogen likes electrons less. Now, there was a chemist who put together a table of what's called electronegativity values to help us figure out which atoms like electrons more and which atoms like electrons less. So electronegativity is a relative measure of how strongly an atom attracts electrons when it forms a covalent bond. So the scale that we use most often for electronegativity is called the Pauling scale, after Linus Pauling. So electronegativity increases going from left to right on the periodic table. So atoms on the right-hand side of the periodic table like electrons a lot more, or they're more electronegative, we would say. And then electronegativity decreases going down a column or group. So atoms that are on the bottom of the periodic table like electrons less. So one way to also remember this is fluorine is the most electronegative atom on the periodic table. Fluorine loves electrons the most out of any atom. And then if we go diagonal to that, francium is the least electronegative on the periodic table. Francium does not like electrons. And this sort of makes sense, right? Remember, the metals are on the left side of the periodic table, and metals typically give up their electrons to form positive ions. So the metals on the left-hand side, they don't really like electrons that much. They don't care about them. They can give them away. But on the right-hand side of the periodic table are the nonmetals. And remember, nonmetals like to gain electrons to become more like the noble gases. So they love electrons, and they want to gain electrons if they can. Now, you'll notice that there are numbers underneath each chemical symbol. So the Pauling scale goes from 0 to 4. So 4 is the most electronegative. And notice that fluorine has a value of 4. And then as we look towards the metals, you'll see that those values are closer to 0. So lithium, for example, has a value of 1. If we go all the way down to francium, that has a value of 0.7. Okay, so we can use these numbers to figure out where electrons are hanging out in a molecule. And that way we can figure out the bond polarity. So which side of the molecule is partially positive, which side of the molecule is partially negative. And later on, that's going to help us determine how molecules attract each other. So that'll become important. All right, so let's look at a table of bond polarity and the electronegativity difference we would expect. So if we're trying to figure out if a bond is polar or nonpolar, we're going to take the difference in electronegativity values between the atoms in the bond. So for example, if we look at just the H2 molecule, what we're going to do is figure out the electronegativity value for each hydrogen. But of course they're the same, so they'll have the same value. So let's go back to our table, and we can see that hydrogen has an electronegativity value of 2.1. All right, so we're going to subtract 2.1 from 2.1, which gives us 0. All right, so that is our electronegativity difference. So if we look, if we look on our table down below, the electronegativity difference between those hydrogens is less than 0.4. So that bond between the hydrogens is a pure covalent or non-polar bond. So I'll also write non-polar here. All right, let's look at a different one. Let's look at HCl. So we already said that the electronegativity value for hydrogen is 2.1. Let's look up the electronegativity value for chlorine. So chlorine is underneath fluorine, and it has a value of 3. All right, so we always want our difference to be positive, so I'm going to subtract the smaller number from the larger number. So we'll subtract 2.1 from 3. And that gives us an electronegativity difference of 0.9. Okay, so let's look down at our table below. So 0.9 is between 0.4 and 1.8. So that means that this bond between hydrogen and chlorine is polar covalent. So that is a polar bond. All right, so the HH bond was non-polar covalent. So electrons were shared equally between the atoms. And the bond between hydrogen and chlorine was polar covalent. So that would be a polar bond where electrons are not shared equally. Now, last but not least, we have the ionic bond. And we would expect the electronegativity difference for that bond to be greater than 1.8. So that would be, for example, the bond between sodium and chlorine. So we already looked up chlorine's electronegativity value. It was 3.0. Let's look up sodium's electronegativity value. So sodium is on the left here, and its value is 0.9. So again, I want to make sure my electronegativity difference is positive. So I'm going to subtract the smaller number from the larger number. So 3 minus 0.9 gives me a value of 2.1. So 2.1 is definitely greater than 1.8. So in our table, that would be an ionic bond. So that's where we have a complete transfer of electrons. So it's not that the electrons are shared unequally between sodium and chlorine. The electrons are fully transferred between sodium and chlorine. Now, I do have a little chart on the left here, just showing kind of a general scheme. So if your electronegativity difference is 0 or close to 0, the bond type is pure covalent, or we also say non-polar covalent. If your difference is intermediate, it's kind of in the middle, then that's a polar covalent bond, and electrons are shared unequally. And then if your difference is really large, that means you have an ionic compound. But remember, you can also tell that you have an ionic compound if you have a metal bonded to a nonmetal, or if you have polyatomic ions present. So let's do some more examples, and let's see if we can figure out whether we have a nonpolar covalent bond, a polar covalent bond, or an ionic bond. And we'll do these ones together. So let's look at HF, hydrofluoric acid. So we said previously that the value or the electronegativity value for hydrogen is 2.1. And we said that fluorine is the most electronegative atom, so that has a value of 4.0. So let's take the difference between those. And 4 minus 2.1 is 1.9. All right, so let's go back to our chart and see how we would categorize that. So looking at our table, 1.9 is greater than 1.8. So would that be an ionic bond? Well, let's see. We have two nonmetals, right? Hydrogen and fluorine are nonmetals. So this shouldn't be ionic. So this is a tricky one. This is one of our exceptions. So this one looks ionic, but the bond is between two nonmetals. So really, this is just a very, very polar bond. So this one's a tricky one because initially we would think it's ionic, but it doesn't have a metal and a nonmetal. It has two nonmetals. So again, this would just be a very polar bond. So I threw this in here just as an exception to the rules we just talked about. But don't worry, all the other ones we're going to look at today follow the rules. All right, so let's look at the second one. We have two chlorines. And earlier we said that each chlorine has an electronegativity value of 3.0. So we're going to subtract 3.0 from 3.0, and that gives us a difference of 0. So how would we categorize that bond? This one would be a non-polar covalent bond, or pure covalent bond. So that means that the electrons are shared equally. All right, the next one, lithium and chlorine. So earlier we saw that lithium has an electronegativity value of 1.0 and chlorine's value is 3.0. So if we take the difference between those, we get a difference of 2. So let's look at our table. So 2 is greater than 1.8. So that means this would be an ionic bond. But let's just make sure. Remember, ions have a metal and a nonmetal, and that is true here. Lithium is a metal, chlorine is a nonmetal, so this would be an ionic bond. So that means that electrons are transferred between the atoms. All right, so you might be wondering, do I have to memorize these electronegativity values? The answer is no. So the chart that I just showed you on this slide here, I will give that to you on an exam. So I'll make a note here. I will provide this chart on exams. And quizzes. If we have a quiz, you can use this chart too. Now, on this next slide, the table here, that I do want you to memorize. So remember that nonpolar bonds will have an electronegativity difference less than 0.4. Polar bonds will have an electronegativity difference between 0.4 and 1.8. And then ionic bonds will have a difference greater than 1.8. So that part I do want you to remember, but the table I'll provide on exams or quizzes. Okay, so now it's your turn to try this on your own. See if you can figure out whether these bonds are pure covalent Again, we call that nonpolar sometimes. Polar covalent or ionic. So pause the video, see if you can figure that out on your own, and then we'll go over it together. All right, let's look at N2, which is a nitrogen molecule. So on our electronegativity chart, the value for nitrogen is 3. So we're going to take the difference between the atoms, and that gives us a value of 0. So how would we categorize the bond between those two nitrogen atoms? Pure or nonpolar covalent. So that means that they share electrons equally. And then what about carbon and oxygen? So carbon has a value of 2.5. Oxygen has a value of 3.5, according to that chart that we looked at. So let's take the difference. And it looks like that would be a difference of 1. So how would we categorize that bond between carbon and oxygen? Polar covalent. So that means that the electrons are shared unequally, or they're not equally shared, however you want to say it. So we could actually draw a little arrow indicating that oxygen likes electrons more than carbon. And we can tell that from the values on the electronegativity chart. So oxygen's value is a little higher, so that means oxygen likes electrons more than carbon. All right, let's look at the last one. So magnesium has a value of 1.2, and oxygen has a value of 3.5. So let's take the difference. So our difference would be 2.3. So how do we categorize that bond? Ionic. So that means that electrons are transferred between the two atoms. And we also can tell this is an ionic compound and an ionic bond because magnesium is a metal and oxygen is a nonmetal. So that's another clue that this would be an ionic bond. All right, so we'll stop there for this video. In the next video, we're going to talk about molecule polarity. So now that we know how to figure out if an individual bond has polarity, now we can apply that to an entire molecule and see if the molecule as a whole is polar or nonpolar. And later on, that's going to help us determine if molecules are attracted to each other or not attracted to each other. So I will see you then.